change of state of matter. Let's take a classic example. So I do have ice at minus 10 degrees Celsius. Mass of ice, let it be, say, 20 gram. What amount of heat I should supply? To bring it to temperature of 0 degrees Celsius. The same ice, 20 gram, it should come to what? 0 degrees Celsius. What amount of heat I should supply? So I'll write it Q1 equal to mass of ice, specific heat of ice, final temperature 0, initial temperature minus 10. I think this formula okay. Mass of ice 20, specific heat of ice 1 by 2 or 0.5. Specific heat of ice is 0.5 calorie per degree Celsius. So this will be 10. So 20 into 5, 100 calories of heat I should supply to rise the temperature of ice from minus 10 to 0 degrees Celsius. Now further I supply heat. What amount of heat I should supply now so that it will melt, it will become 20 grams of water at 0 degrees Celsius. So what is the process now here? Melts. Melting of ice occurs. So for that I should supply heat, no? I'll put that arrow here. So here what's happening? If you supply heat, temperature of body increase, no? Here I supply heat. So what is the state of this? This was a solid state, no? Ice will be solid. And what is water? Liquid. So what's happening? The substance from solid state, it is changing its state from solid to liquid. And what's happening to temperature? Temperature will not change. So the ice is melting here. So there's a change of state occurs. The matter is changing its state from solid to liquid. But what happened? Temperature will not change. So therefore, shall we put like this? If a body gains heat, temperature must increase. What do you say? Maybe. If a changing state, need not be that one. So what all heat we supply, that will be utilized only for change in state here. So what is this Q now? Q2 should be equal to mass of ice into latent heat of fusion. So this is called as latent heat of fusion, it is called as. So what is the value of this will be 80 calorie per gram. The value of latent heat of fusion for ice will be 80 calorie per gram. So how we define latent heat? Amount of heat required to melt m grams of amount of heat required to melt m grams of substance is called like a latent heat of fusion, that one. Because how you define LF? LF should be Q by amount of heat required per unit mass to melt that particular substance is called like a latent heat of fusion, that one. So there won't be change in temperature of a substance. What all we supply it here, what all we supply heat, it is utilized to rise the temperature. What all you supply heat, it is utilized to change state of matter. From solid, it will become liquid state here. So when a substance changes its state, no change in temperature. So what is the conclusion we can make it? When a substance changes state, temperature will not change. No. Similarly, if water freezes to ice, what should happen? So let's make it generalized here. If there's a ice, for it to become water, temperature I'm indicating here, we should supply heat, m gram. So what is Q equal to? M into LF. This is called like a melting. Similarly, water at 0 degrees Celsius, for it to become ice at 0 degrees Celsius, you have to take out heat. The heat has to be extracted. So if you take out heat, then what happens? The water will become ice. So this, what we can call this process, is called like a freezing. Agree this? This process is called like a freezing here. So similarly, so we'll go for water at 100 degrees Celsius. Water at m grams of water at, I'll supply heat, or say it will change its state to vapor or steam, anything you can write, better write vapor, m grams of vapor at 100 degrees Celsius. So for this, I'm going to supply an heat. I'm going to supply it here. Now, what will be, so this particular thing, so shall we call this as vaporization? In this case, what is the Q? Mass of water into latent heat of vaporization. What is LV? Latent heat of vapor. Its value will be 540 calorie per gram. Similarly, water at if a vapor at 100 degrees Celsius, if it becomes water at 100 degrees Celsius, so this is called as a condensation. So what is the value again? Q equal to mLV, that one. Heat will be rejected. For vapor to become water at 100 degrees Celsius, it has to give out heat. If it loses heat, no, so then the vapor will get condensed and will become water here. So again, the formula will be this one. I think we'll be widely using this particular formulas, Okay, let's take some small example. I think you might have come across this in chemistry. Let me have water. You can see all this. Okay, let's do one thing. I have high side mass of ice, let it be 20 gram. It is at say like a minus 15 degrees Celsius. What is the temperature? First, it will become water at, so 20 gram of water. What is the temperature? 0 degrees Celsius. Then I will write this temperature to how much? 100 degrees Celsius. Then I'll convert the whole thing into vapor. What is the amount of heat I should supply? So first here I'm going to start like this. So here Q1. So okay, this one block is missing. Okay, thank you. We'll make ice. Then it will melt. Yeah. So I should supply heat here Q1, Q2, Q3, Q4. For ice at minus 15 degrees Celsius to convert into vapor at 100 degrees Celsius, what amount of heat I should supply? So I'll start with this one. Q1 equal to mass of ice, specific heat of ice, 0 minus of minus 15. This should be equal to 20, 0.5 into 15. 150 calories Q1. Then Q2 equal to mass of ice into latent heat of fusion. 20 into 80. 1600 calories. Q3 equal to mass of water, specific heat of water, 100 minus 0. Mass of water, the same, 21. The specific heat of water is 1. This is 100. So this will be 200 calories. 16. Then what is Q4? Mass of water into latent heat of vaporization, 20 into 540. This will be 12800 calories. What is the total heat? 108. 10800. What is the total amount of heat I should supply? I should add up all the total heat, Q1 plus Q2 plus Q3 plus Q4. $12,000, 12, 13. 14,150. So this much of amount of heat I should supply. Let's plot the temperature versus heat input. What are Q1, Q2? Heat supplied or heat input. Shall I call total heat input? I think like this, the calculations will do. Let's go for plotting graph. So what is a graph? I'm trying to plot temperature versus the heat input. And this is the temperature in degrees Celsius. So this will be 0, minus 10. So first, the temperature of the substance will increase. Let me take different colors. Then it will become 0. Okay, I do have like this, the graphs. So So this is dotted line. We'll take it here. I think let me go for some thick lines. Yeah, this will be. Oh. This graph very important. Lot of information every time. Instead of in numerical struggling, no, the graph will speak. It will give a lot of information regarding that particular substance. So we do have this particular thing. So first I'll start with this is O, A, B, C, D. This is for what? The above sequence. What that happened above sequence, no? I think able to see this. I think more than this not possible. Try to see this. This is the EAT input. Let me write it here. What will happen? The temperature of the solid state. No, what is OA? Solid state. What about AB? It will change state. No, from where? From solid to liquid. From solid to liquid. So therefore, this is the minus 10 degrees Celsius. Then what we get? This is 0 degrees Celsius. This is 100. If I take the slope of curve OA, what it should be, that one. Let me write it here. Degree. Yeah. O means not 0. O means some symbol. OA, that one. What is that OA? OA will give us the something like a where temperature of ice is increasing. No. So if I calculate the slope of that, what we get? So, and this is Q1. This is Q2. This is Q3. This is Q4. If I calculate slope, so what do that slope will give? dt by dq. So what is the slope of OA will become equal to? Slope of line OA should be equal to dt by dq. This should be reciprocal of, will you agree this? Reciprocal of thermal heat capacity of the substance, because what is mass into specific heat? Should be thermal heat capacity, specific heat capacity, thermal heat capacity. Specific heat capacity means only S. Thermal heat capacity means mass into specific heat. So therefore, here the slope of this line will be the reciprocal of, or so like the slope of this line will become equal to reciprocal of thermal heat capacity. What do the line AB indicates? Change of state. So greater the value of, greater the, if the length of this line, so more heat is required, no? So this will be the change of state, that one. So here what we have, we can write it as this is solid. Liquid. Further, if you want, you can go for vapor. Okay, this is a vapor state. Okay, now try to see this. This is a liquid. This is a vapor. What about this? This will be, shall I say, here melting of ice takes place. Here vaporization occurs. So what do this horizontal line indicates? Greater this horizontal line for a substance, so more amount of heat is needed. Or definitely what you can say, latent of vaporization is more. If CD greater than AB, what does it mean? Latent heat of vaporization is more than that of latent heat of fusion. If CD equal to AB for two substances, then S latent heat of vaporization is equal to latent heat of fusion. Like that, if I plot temperature versus heat input graph, it is giving us lot of information. Okay, next again, you will do one thing. Let me write, this is say alpha 1, slope, no? So this is, shall we write equal to tan alpha 1? If I give this alpha 1, with this what you can calculate? The thermal heat capacity. Then again, what is tan, like a slope of line OBC? It's also dt by dq. Similarly, you can go for the vapors. Oh, vapors, okay, we'll discuss later on. Let's not say. So now if I say that alpha 2 greater than alpha 1, what do you mean by that? Specific heat of substance in the liquid state is more than that of specific heat in the solid state, because mass will be same, no? See, when the substance changes state from solid to vapor, what will happen to mass? Everywhere mass will be same. Everywhere mass will be same. So what do this particular angle will give us information? Tan of this angle. Tan of this angle. It will give us information regarding the specific heat substance. Suppose say there are substances are there where alpha 1 greater than alpha 2. Then the specific heat of substance in solid state will be more than that in liquid. If alpha 1 equal to alpha 2, then the substance will have same specific heat in both the states, solid and liquid. Like that in this graph, this horizontal line will give us information of latent, this will give us information of latent heat of fusion, this horizontal and latent heat of vaporization. The slope will give us the information of specific heat. Able to get this one? So I have just dumped information in the form of this one. So they may give graph, they may give this, they'll give mass of the substance. So with this, you can calculate specific heat of substance because tan alpha, you know value, you get the specific heat. Getting the idea? So these are the methods what happen you should able to apply here. Huh? 14.550. Yeah. Yeah. Okay. Thank you. AB and CD. What are AB and CD? Latent heat of fusion. What is this Q2? What is Q2? You have formula. Look at here. Make observation. Change of state. No. So this will give information of latent heat of fusion. What is Q4? MWLV. Latent heat of vaporization. Mass of substance will be same. No. So the ratio of CD by AB, what should give? LV by LF. Make observation, graphs, interpretation of graphs. So like that, what happened? The idea of like this, we do get here. Means now you have to ask question like the heat supplied, it is utilized to rise temperature. Here the heat supplied, where it has gone, it is utilized to change the state of substance from solid to liquid. That is the thing. So wait, how it is available? Okay, here rise in temperature. What about here? It be converted into increase in potential energy of the substance. Because as the distance between atom increases, the energy should increase. What is the reason? How do we can claim? I think there's a graph. Look at this graph, what this graph says. energy, potentially or whatever. So when you supply heat, nothing but what happen, you are increasing the energy. So what happened? The distance between atoms will increase, no? This is what happens. So we know that compared to solid, the distance between atoms in liquid will be more. Compared to liquid, the distance between atoms will be more in the vapor, in gaseous state. So what actually, when we supply heat, so what that solid will do, will increase the distance between atoms. Then from solid will become liquid. So we know that solid and liquid state of that one, the distance between atoms in gases will be more than that in the liquid. And the distance between the atoms in the liquid will be more than that of solid here. So what actually we are supplying it, what it is being done, it is utilized to increase the distance between atoms. Therefore, here if you supply heat, it is utilized to rise the temperature. Rise the temperature means what? When the atoms will start vibrating. More rigorous, the atoms will start vibrating as you rise temperature. Then at one specific temperature, so what happens? The distance between atoms will increase. Then it become a liquid. Then again you start rising temperature. Again the atoms more rigorously they'll be moving. So then at one specific temperature, what will happen? The liquid, what happen? The substance will change its state from liquid to vapor. Sorry, is it all substance will at 100 degrees will change state? No. It all depends upon the material. What we are discussing is for water. So some liquids are there where they'll get vaporized at 150 degrees Celsius, 200 degrees Celsius. We are discussing here for water. So what is this graph? For water at 1 atmospheric pressure. At 1 atmospheric pressure. Getting the idea? These are the okay. Any doubt? Any doubt? Before that, today, okay. I'll give the Ansika ready.
Yes, sir.
Today at after 1:10, you can call me. Huh?
Yes, sir.
You'll be free at that time. Any classes will be there?
Sir, after chemistry class, I'll call you, sir.
Okay, that one. Yeah, one. My class will get over at 1, but for seniors, I'll be taking class. No, therefore after 1, I'll be free. Huh?
Yes, sir.
Okay, that one. After this, I'll give five more. Abhiraj Mahajan.
Sure.
Okay, after again after. So you do one thing. 1:10. Ansika ready. You call me at 1:10 or in that. Huh?
Yes, sir.
For 10 or 5 minutes we'll talk because I have to talk with many other kids. No,
Yes, sir.
Abhiraj Mahajan, you can call me at 1:20.
Yes.
Next, Akash Sridhar.
Yes, sir.
1:30 you can call me.
Okay, sir.
Then we have who are there on top? No, this one Vardhan Yashovardhan completed.
No, sir.
No. Yashovardhan, you can call me after 1:30.
Yes, sir. Okay, sir.
Just you do one thing, all of you, just like it with in WhatsApp, no, you just send your name so that I'll tell like you can call me now. We'll have communication like that. After class, no, you can send your name, sir. I am so and so person. I'll just give time after 1 o'clock. Roughly, I'm giving now because sometimes when I'm talking may extend 2-3 minutes. No, it will be. You can call me after 1:40 something. Next, what we have is next we have Ananya. Ananya, not there. Ananya Junior C double star. Okay. You can call me after 1:40 ma. So in WhatsApp, all this I think 5 students got over. all these 5 students, okay, just in WhatsApp with your name, WhatsApp, type your name and just say like a hi sir. So I'll only call. You need to call, I'll only call it. These are the times. Within that time, what happened will interact. Fine.